In order to find a resultant force in 3D, you have to follow some simple steps. Usually you want to break up the forces into components x, y, and z, add the respective components together, use Pythagorean theorem to find the magnitude, find the coordinate direction angles to indicate the direction of the force resultant. Now here's an example problem that we will be looking at. We have two forces that are acting in the indicated directions, and we are asked to find the force resultant and the coordinate direction angles. But before we do that, I'm going to take you to SOLIDWORKS so you can see what is actually going on with these forces. Here's the example problem that we are looking at to understand more clearly. Here's our force 1 and the corresponding alpha, beta, and gamma coordinate direction angles. And here's our force 2 with the corresponding triangular descriptions. We're going to look at each of these objects in 3D and hopefully help you understand and visualize them better. Force 1 may look like a bit of a mess right now, with all these fancy semicircles rotating about it. But in actuality, it is just trying to tell you the angle from each respective axis, x, y, and z, to the force. These can be used to make triangles. I'm going to show you each of these triangles now. First, I'll disable force 2 so that there isn't any confusion. I'm going to go out of order and start with the y component of force 1. For this, we will need to look at the plane that is created between the force and the y-axis, which will be like this. And then I'll disable the other angles to help us see the beta more clearly. Now when we look at the force this way, it doesn't look as complicated. If we connect a line from the force to the y-axis like this, we can see a right triangle. With this right triangle, we are only really interested in the adjacent leg of the triangle. So we can find that adjacent leg if we were to take the cosine of beta with the hypotenuse, which is the force. Now we're going to look at the z component. Now like we did last time, we're going to go ahead and disable all these other coordinate direction angles. And similarly to last time, we're going to go ahead and draw a line that connects our force to our z-axis. And as we can see, we make another right triangle between the z-axis and the force, and all we need to do is take the cosine of the angle gamma and we will get the z component. Finally, we're going to look at our x component. This one's a bit more tricky than the other components because it is greater than 90 degrees. First, I'll go ahead and disable the other angles, and now we can go ahead and solve this. First thing I want you to notice is because the 90 degrees is greater, that means that the x component is going to be negative. If we can imagine extending the x-axis out in the negative direction, we will get a little triangle that looks like this. And with that triangle, it's still a right triangle now. And all we have to do is take the cosine of our angle alpha, and because the angle is greater than 90 degrees, it will give us a negative x component. We could, of course, take 180 degrees and subtract alpha from it, and then use that to find the angle. That would give us this little angle right here. But you then just have to remember to make your x component negative after those calculations. Now we're going to look at force 2. First, we're going to go ahead and disable all the components of force 1 and just look at force 2. When we look at force 2, I always look at each triangle separately. First, we will look at the triangle that directly touches the force, in this case, the bluish-green one. When we look at the force like this, we will see another right triangle. If you notice, our z-axis is parallel to one of the legs in this triangle, right here. That is an indication that this is in fact the z component. We should also note that the direction that it is going. Since it is going below the xy plane, the z-force will be negative. This will be true for any 3D problem explained in this manner. Pay attention to the direction of the forces when indicating if it is positive or negative. When we try to compare our x and y axis, however, there aren't any values that are parallel. It might be hard to see them from this point of view, but don't forget what the triangle really looks like. When we look at the main view of the object, we can clearly see that the line that slightly appeared to be parallel to the x and y axis isn't. When we're in this view, it is pretty simple to find the z component. It will be the hypotenuse, the force in this case, times the sine of the angle of 25 degrees. To find the other leg would be the hypotenuse times the cosine of that angle. Now you might be curious why the other leg of the triangle is important. Well, when we go out to the main view again, we can see that that leg is actually the hypotenuse of the red triangle. That means that when we are wanting to get our x and y components and values, we're going to need that leg because it becomes the new hypotenuse. I usually call that strange leg my force prime value or my force xy value because it is an intermediate step to finding the final components. Now to find our x and y components is pretty simple. Here we can see solely the red triangle, which has our x and y values. And of course it has our force prime or force xy value from previously. When we want to know which leg corresponds to which component, simply remember that it will be the leg that is parallel to that axis. As you can see, the y component will be this leg since it is parallel to the y-axis. And the x component will be this leg since it is parallel to the x-axis. So now we would just have to take the sine of 35 times the hypotenuse, which is our force prime value, or force xy, and we'll get our y, and the cosine of 35 times the hypotenuse to get our x component. Now we've been able to visually see all the components of these two forces. We can go ahead and do the math now. First, we have to break up both forces into x, y, and z components. This is an easy process. As we remember from the 3D explanation, we can find the components of force 1 by simply taking the cosine of the angle and multiplying it by the magnitude. Next, for force 2, we will use those two triangles. We have to find the hypotenuse of the red triangle, which is the cosine phi of the magnitude, in order to find our xy components by using the sine and cosine of theta. Then the height of the green triangle, sine phi, will be our z component. Now that we have the two forces broken up into x, y, and z components, all we have to do is add them together, and we get our force resultant. Then to find the magnitude, we just need to use Pythagorean theorem, and we can find the magnitude of the force resultant. So I'll go ahead and do that right now. To find the coordinate direction angles, we need to work backwards and take the cosine inverse of each of these x, y, and z components over the respective magnitudes. So for alpha we get 62.8, for beta we get 29, and for gamma we get 80.8 degrees.